In the previous video, we focused on the dot product, and now we will continue with the cross product. We will start with a quick recap from the previous video, as we did introduce the cross product there. Start by adding the vector A, which we can place in the xy plane. We will also introduce the unit vector A hat, which is parallel to A, and the unit vector A n hat, which is orthogonal to A. We can then introduce the vector B, which can be expressed either in terms of our xy basis vectors, or we can express it in terms of our A hat and A n hat unit vectors. When using the A n basis vectors, we get that the A hat component is the part of B that is parallel to A, and the A n hat component is the perpendicular part. We can also introduce the angle theta between A and B. In the previous video, we defined the length of the cross product as the length of A multiplied by the perpendicular part of B. And B perpendicular is the length of B times sinus theta. We also derived that expressions in terms of the x and y coordinates is ax times by minus ay times bx. This was achieved by rotating the coordinate system to make the first vector parallel to the first base vector. To get a geometric interpretation, start by drawing the parallelogram that has vectors A and B as sides. We know that the area of our parallelogram is the base times the height. Here, the length of A is the base and B perpendicular is the height. Hence, the area of this parallelogram has the same value as the length of our cross product. What we also remember from the previous video is that this area is the determinant of the matrix generated from A and B. This would be an alternative way of calculating the length of the cross product without using the angle theta. If we consider 3D, we realize that there are two parallel directions while only one perpendicular. Hence, it could be useful to include this direction information in the cross product. If I think of the parallelogram, we could consider it to be a surface. And for surfaces, we use the normal vector to define the direction. Therefore, we will define the direction of the cross product is the normal vector of the parallelogram generated by A and B. As the surface in the figure is in the xy plane, its normal direction will be in the z direction. The vector we see in the figure is the cross product of A and B. Its length is the area A, and its direction is the normal vector of the surface. Note that the cross product of A and B will be orthogonal to both A and B. I'm going to skip the full derivation of how to calculate the cross product in 3D and only give you the final method. One way to remember the expression for the cross product is to use the determinant. Write the three unit vectors on the first row, the first vector on the second row, and the second vector on the third row. The first term in the determinant is the unit vector x hat multiplied by the 2 by 2 determinant of the other directions. Repeat for the y hat term. Multiply by the 2 by 2 determinant. And for the z hat term, with the final determinant. This trick works as both the cross product and the 2 by 2 determinant describes the area of the surface created by the vectors. The cross product requires that the unit vectors follow the right-hand rule, which means that the cross product of x hat and y hat is z hat. Or, place your thumb of your right hand in the direction of the first vector, your index finger in the direction of the second vector. then the middle finger will be in the direction of the cross product. The next property is that the cross product is anti-commutative. Take a look at the Z value. If we were to swap places with A and B, the expression would change sign. Hence, we can write that A cross B is minus B cross A. This would also follow directly from the right-hand rule. If we take the cross product of a vector with itself, there is no perpendicular part to multiply with, and the result is 0. The 0 vector is a bit special as it does not have a given direction, but we still call it a vector to allow us to use it as input to other operations that require vectors. If we take the dot product of any vectors A and B with A cross B, the result will be 0. This is a direct consequence of that the cross product is orthogonal to both A and B, and the dot product with the orthogonal vectors is 0. Next up is to check our bilinear property. Start by taking A cross K1b plus K2c. As each term is an ordinary scalar operation, we can distribute A. And repeat for the remaining 5 terms. Let these swap position. And distribute the unit vectors. The constants can be placed in front. The first part can be identified as K1 multiplied by A cross B, and the second part as K2 multiplied by A cross C. And we get the linear property that we can place the cross product inside the parentheses. The next operation is the dot product between A cross B and the vector C. This operation is easiest to understand visually. Start by creating the cross product between A and B. We know that its length is the area A and its direction is n hat, which is perpendicular to both A and B. Now add the third vector C. We can write the expression as A n hat dot C. Let's introduce the coefficient C parallel, which is parallel to n hat. The final value should therefore be A times C parallel. Let us introduce the volume that has the 3 vectors A, B, and C as sides. This volume is a parallel epipede for which the volume is calculated as the base area A times the height C parallel. Hence, we can make the geometric interpretation that A cross B dot C is the volume created by the 3 vectors. If you remember the previous video, we had a different method for calculating this value, which was the determinant. This offers an alternative approach for calculating A cross B dot C. From this geometric interpretation, we can also realize that any cyclic permutation of the 3 vectors should give the same volume. The determinant also stays the same if you do cyclic permutations in any direction. Be aware that the cross product is anti-commutative, so if you change the order of the cross product, you will get the negative volume instead. The cross product is not associative, meaning that A cross B cross C is different from A cross B cross C. A simple way of realizing this is to consider what happens if we make A and B the same. B cross B would be a 0 vector, making the right-hand side 0. The left-hand side is non-zero, which we will see in the following example, where we are going to derive the expression for the vector triple product. Start by drawing the vectors b and introduce its unit vector b hat. Add the vector c with a different direction. Introduce c perpendicular as its perpendicular projection with respect to b. And introduce the parallel projection as c dot b hat, as we learned in the previous video. Using basic vector subtraction, we can write the perpendicular vector as the difference between the parallel projection c dot b hat and the vector c. Remember that this vector has length c perpendicular. Let us start by taking the cross product b hat cross c. As we defined b hat cross c as the length of b hat times the perpendicular part of c. We can use that b hat has unit length, and hence the length of b hat cross c is c perpendicular. Let us call the direction with the cross product n hat. We see that b hat cross c has the same length as the perpendicular vector, but a different direction. To fix this, we can take the cross product with b hat for both sides. B hat will be perpendicular to n hat, hence b hat cross n hat will have length 1, and the new vector will have the same length as before, but the new direction will be perpendicular to both b and b hat cross c. Hence, these two vectors will now be the same. This means that we can identify the right-hand side as the c perpendicular vector in the figure. As we don't want to be limited to unit vectors, we can multiply both sides with the length b squared. And use that b hat is the vector b. We can also write b squared as the dot product b dot b. This is the value of b cross c. However, it would be good to have an expression without the limitation that two vectors have to be the same. Start by noting that b and c are arbitrary vectors, hence the expression should be correct if they swap places. Use that the cross product is anti-commutative and swap the order of b and c. Now we have expressions for b cross c and c cross c, but we want to make it more general. Use that the cross product is linear and multiply with an arbitrary constant a1. As a1 is arbitrary, we now have an expression for the cross product of any vector parallel to b with the b cross c. Do the same and multiply by a2. Note that the only difference between the two equations are the terms where the constant appears. Hence, we can use linearity and add the two lines together. Now, we have an expression for the cross product of a1b plus a2c with b cross c. But what does this mean? Let us first draw the vectors b and c, and then add an arbitrary vector in the same plane. Since a1 and a2 can have any value, we can adjust the values of these to make a1b plus a2c equal to this vector. This will work for any arbitrary vector in the BC plane. This means that we have an expression for how to take the cross product of any vector in the BC plane with b cross c. But to make the expression work for any vector, we need to add an arbitrary constant multiplied by a vector in the third direction. To get the third direction, use that b cross c is orthogonal to both b and c. Add in a constant a3 multiplied by the third direction to this term. To motivate why this is allowed, note that the cross product of b cross c with itself is 0. Hence, we have just added 0 to the equation, and it should still be valid. Add the term for the third direction to these as well. Once again, we have only added zeros. B cross C is orthogonal to both B and C, and hence the dot products are 0. Finally, as A1, A2 and A3 are arbitrary constants, this could represent any vector. Rename it to A. And reorder a bit. The reason I reordered the expression is because this is a common way of writing the formula called the back cab rule. And it states that A cross B cross C is B multiplied by A dot C minus C multiplied by A dot B. To do a graphic illustration, let us show it when using B hat and C hat as two of the vectors. Start by drawing B and C and add the cross product B hat cross C hat. Now introduce the third vector A. The red dashed line is drawn perpendicular to both A and B hat cross C hat. The final result is expected to be somewhere along this line. Draw the projections of A on B and the projection of A on C. Next, insert the term B hat A dot C hat and the term minus C hat A dot B hat. A cross B hat cross C hat will now be these added together. We can see that it ended up on the perpendicular line, as expected. This will mark the end of our vector algebra exercises. Let's do a quick summary of the most important results. The cross product of A and B is a vector with length equal to area that is created by the two vectors A and B. Its direction is normal to the surface and will be perpendicular to both vectors A and B. If you need to calculate it, you can use the equation I've written on the top of the screen. The direction of the cross product follows from the right-hand rule, which also has the consequence that if the vectors swap places, we get the opposite sign. Another way of viewing the cross product is that it's multiplication between the perpendicular parts of two vectors. This means that its maximum value is obtained for perpendicular vectors, and if the vectors are parallel, it is 0. If you take the dot product of A and B with the cross product of A and B, it is 0 as the cross product is perpendicular to A and B. The cross product is linear. We finally derived the vector triple product, which is the famous back cab rule. We also derived the scalar triple product, which is the volume created by the three vectors, or alternatively, their determinant. We will now continue to applications of the cross product. The first application is rotating systems. Start by creating an object that will be moving around the circle. The radius of the circle is r, and we can add the rotational velocity omega, as well as the axis of rotation, which is pointing towards us in the figure. We can introduce the velocity v of the object, and you're hopefully familiar with that v is omega r in the tangential direction, which we call phi hat here. Let us study the directions in the expression for the velocity. We have that all three directions are orthogonal. As v is orthogonal to both the radius and the axis of rotation, this seems very similar to a cross product. And we can instead write v as omega cross r. Now you may ask, why did we do this, as r omega phi hat was a simple expression to work with? But consider the general case where the axis of rotation no longer is aligned with one of the unit vectors, and the object may not rotate around origin. Here it can be more convenient to use omega cross r. Moving on to our next example from mechanics, which is the bending moment. Assume that we have a flat plate that can rotate around its center. Add an object to the right side. Assume that it has a force of gravity pointing down. The horizontal distance from the center of rotation to the center of gravity is r. This would give the bending moment m equals minus r Fg z hat. If you wonder why it's negative, it comes from the right hand rule. Place the thumb of your right hand in the direction of the axis of rotation. Positive direction will then be in the direction of your other four fingers. If this system would be allowed to move, it would cause the plate to tilt to the right. As the bending moment is multiplication with perpendicular vectors, it can be written as a cross product. First, change the vector r to start from the center of rotation. We can now change the equation for the bending moment to be the cross product between r and the force Fg. We no longer need the minus sign as the cross product handles the sign for us. To illustrate how we can use the cross product more, add in a second weight at a different distance r2. If the combined bending moment of both objects is 0, the plate is balanced. Otherwise it will rotate. Assume that we have placed the second weight in the correct position to create a balanced system. The next question is it stable? And what do we mean by that? Assume that we disturb the system by moving it in one direction, here, tilt to the right. If the system rotates back to its starting position, it is stable. If it stays tilted, it's not stable. Note that when we tilted the plate, the angle between the r vector and the gravity has become closer to perpendicular. This means that the first weight has a larger bending moment now than at the starting position. For the second weight, its r vector and gravity are closer to being parallel than at the start. Here, the cross product will give a lower value and therefore a lower bending moment. The conclusion is that the plate will remain in this position. Let's try and give it a push to the other side. This will cause it to tip over to the other side. Now, it's the second weight that has the r vector closer to being perpendicular, and the first weight has the r vector more parallel to gravity. Hence, the weight on the left creates the largest bending moment and the plate will stay in this position. We will need to give it a push to return it to the base position. We can therefore determine that the position is unstable, as it does not return to the original position by itself. The next question is, how do we make it stable? One solution is to put the weights under the plate instead. Now when we tilt it, the weight to the left is closer to having perpendicular vectors and gives the largest bending moment, while the weight on the right gets a lower bending moment due to more parallel vectors. In this case, we can expect it to turn back by itself. With this example, I will end the video about cross products. Next up will be dyadic products and tensors of rank 2. Thank you.